Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and today, as you can see, I'm bringing to you all a new Biology 1 episode. This one is going to be the last video in our little series on the process of science. So in this series, we've pretty much been talking about the scientific method, especially in the first video. We also talked about components and vocab words that are going to come up when you talk about experimentation, such as experimental group, experimental factor, the control group, constants, independent variable, dependent variable, all these different things. So we covered that in the first video. And then in the second video, we focused more on the experimental design. So knowing all this, knowing the scientific method, how do we actually design a unique experiment that will address our question and that will hopefully either help us accept or refute the hypothesis we came up with? If you haven't watched those, I would highly suggest you watch them, because in each of these videos, I'm building off of what we learned in the last video. So that last video about experimental design will be linked in the description box below. And if you want to access the first video, you can go check out our Biology 1 playlist at our YouTube channel. As you can see, today we're going to be focusing on the third part of the process of science. So now that we've observed our surroundings, asked a question, done some background research, formed a hypothesis, identified components of our experiment, developed a procedure. Now we actually have to execute the experiment. So I'm not going to be talking about the same experiment I did in the last video, if you watched it, where we talked about apple trees and orchards and gauging the health of a fruit and the impact that different amounts of plant fertilizer can have on those apple trees. In this case, I'm going to be talking about a type of experiment called a double-blind experiment. And if you don't know what that is, that's fine. That's exactly what I'm going to cover in this video. And if you're confused and you're thinking, Anita, why do you have a bunch of pills as the picture for today's lesson? Well, the lesson today is going to discuss an experiment commonly used in the medical field regarding testing new medicines for diseases. So today we're going to be talking about the execution of our procedure, so how we actually execute the experiment we came up with, and afterwards how we collect our results, analyze our results, draw a conclusion, and then hopefully develop a theory that may one day become a law. So let's get right into the lesson, but before I do, I would really appreciate it if you could hit the pause button and quickly give this video a like, also subscribe to our channel, and hit the post notification bell. Don't feel afraid to drop a comment down below. We really want to hear what you all have to say. And lastly, please share the video. Okay, so like I said in that intro slide, I mentioned something called a double-blind experiment. So this is a type of experiment that I do want to discuss, because you might hear this, especially when you're thinking about like clinical trials. Like I said, this video is focused a lot on actual like real world situations. Obviously, in a classroom setting, when you're doing an experiment, you're probably not going to do a double-blind experiment, because I can't think of a situation in a biology class where you're going to have to worry about something like this. And you'll see what I mean when I explain what it is. However, like I said, you might see this if you go into the medical field and you do if you're more into research and you're testing drugs on patients. And that's an example of experiment, because you're trying to see the effect that a drug has on varying patients and on the diseases that the patients might have. So a double-blind experiment will come into play in clinical trials, and it's important that you all know what a double-blind experiment is, because this is what we usually in the real world. So a double-blind experiment is an experiment in which the experimenter does not know which group is which, the experimental group or the control group. So when I say experimenter, I want you all to think of a doctor or a researcher who's come up with a pill that they think will cure a disease. So after they come up with this pill, they obviously need to test it on people before they go out into the world of science and declare that they have found a cure to so-and-so disease. Obviously, they need to do experiments, collect results, see if this pill is actually effective. So the experimenter, think of that person as a doctor or a researcher. So when this doctor or researcher is going to conduct a trial, obviously, since they're the ones who developed the product, which is the pill, and let's think of the medicine as a pill in this case. So because the doctor or the researcher developed this pill, they obviously want the pill to succeed. So they want the pill to show effects of of curing the disease in patients, so they obviously want the pill to be successful. Therefore, because they really want the pill to be successful, they can be a little bit biased. So bias is pretty much when you incline towards one way. So when you favor something over another thing. So in this case, the doctor or researcher is going to favor a positive result, meaning that patients with the disease have been cured after taking their pill, versus a negative result in which patients were not cured after taking this pill. They obviously want their product to be successful, and that can cause bias. So an experiment can be conducted that is unfair and that can skew the results. So even if the pill wasn't actually successful, because the doctor or researcher wants to portray it as successful, the results can be skewed and there can be bias, and this can be detrimental because people will not get an effective medicine, and this can just lead to catastrophe. So that is why double-blind experiments are used. So like I said, experimenter is the doctor or researcher. In this case, the doctor or researcher does not know which group is which. So remember from our last video where we're talking about the apple trees. One of those groups we allotted as the control group. So that control group did not get any fertilizer. We treated them as plants that live normally in nature, don't get any man-made fertilizer. We had 3 other groups. The first group, I believe, got 1 cup of fertilizer, our first experimental group, because remember our experimental factor, which was our independent variable, was the fertilizer. The first group, our first experimental group, got 1 cup of the experimental factor, so 1 cup of plant fertilizer. The second group got 2 cups of plant fertilizer, and the third group got 4 cups of fertilizer. So we were doubling it as we went higher and higher in the experimental groups. We had 3 experimental groups and 1 control group. Usually in in these medical trials, you have 2 groups. You'll have 1 control group and then 1 experimental group. So the control group does not get the pill, and then the experimental group will get the pill. So in this case, the experimenter, who's the doctor or the researcher, they get people to be part of this study. So regular people like you and me, they get us to be part of this study, and usually we carry this disease or whatever they're trying to cure, and they split us into 2 groups. One is they don't split us into 2 groups. They will give us a pill. Let's put it that way. Let's say they collect 200 people. They will give each person a pill. However, so there's going to be a total of 200 pills. However, 100 of those pills are actually going to be the medicine, whereas the other 100 of those pills are just going to be like a sugar pill, so they don't do anything. It's just made to look exactly like the actual medicine, but it doesn't do anything. So the sugar pills, the fake medicine, if you want to think of it that way, will be given to half the people. Then the actual medicine will be given to the other half of the people. In this way, even us, the patients, and the experimenter who's conducting this experiment involving us, both of us don't know who the experimental people are and who the control people are. So if I'm taking the pill and I'm part of this experiment, I don't even know if I'm taking the actual pill. I might be taking a sugar pill, or I might be taking the actual pill. So we don't know. That's why it's called a double-blind experiment. The experimenter doesn't know if an individual, a test subject, belongs to either the experimental group or the control group. And I, the test subject, also don't know if I belong to the experimental group or the control group. So that's what a double-blind experiment is. And the main purpose, like I said before, it eliminates bias on the part of the experimenter. And if you see down here, I put a picture of a girl with a blindfold on. Oftentimes in science class, when they're introducing you to this concept, they'll show you pictures of people blindfolded. This is just a way to emphasize that there is no bias, because you can't see anything. And if you can't see anything, then you can't really be biased. So it's just like a little analogy. It's a way you can remember it. So double blind. You're blind to the bias. Now I want to talk about double-blind tests. So this is actually conducting the double-blind experiment. So in this case, I have a lot of stuff on this slide because this is very important. So double-blind tests are actually when you incorporate the double-blind experiment into your own experiment. So these tests are used when patients or the data recorder may bias interpretation. So in this case, think of the patient as me. I'm the test subject participating in this clinical study, and then the data recorder, who's the doctor who actually developed the medicine and who's recording the data. Think of them as the data recorder. In this case, we use double-blind experiments because of the off chance that maybe I will bias the results, or the doctor conducting the experiment will bias the results. Like I said, maybe the doctor ends up if this wasn't a double-blind experiment and the doctor really wants to prove to other scientists that his or her medicine is effective on the very first trials that he or she is doing, maybe he or she will pay me to pretend to pay me to skew the actual results so that I make it look like my this medicine was actually effective and helped me combat my disease. In that case, that would be bias. So in this case, we use double-blind tests to make sure that I am not biased and the doctor or researcher who's conducting the study is not biased either. Just like double-blind experiment that I explained on the last slide. So here we assign treatments randomly. One group gets drug and one group, the control, does not. Like I just explained on the last slide. I actually got ahead of myself a bit there. So like I said, I want you to imagine this. A doctor has come, let's call it a her. The doctor, she has come up with a pill to combat so-and-so disease. And she wants to conduct an experiment. So she gets 200 people together, all volunteers who have this disease. And she has them come to her lab one day. She has them all stand in a line. So 200 people are in a line. They're all lined up in front of a table. And at that table, another researcher has 200 little containers of pills so on that table, and these pills are just randomly placed on the table. Some of them have the sugar pills that I was talking about, the ones that don't do anything. They're just supposed to be administered to the control, and then the other half have the actual pills with the medication in them. And what happens is the person sitting at the table, who also does not know which containers contain which kinds of pills, is just handing these pills as the people come towards him in the line. So, like I said, think of people in a line. Each one is stepping towards the table, taking a container from the person sitting at the table, and then going on their merry way. And then, let's say for the next month, they're going to take that pill every morning before breakfast, and then after that month, results will be recorded, and then that's where we can analyze the results. So that's what I mean by assign treatments randomly. So this person at the table is just giving random containers of pills to these people lined up. All we know is that there's an even amount of sugar pills and actual medication. So 100 of those containers are going to have the sugar pill, the ineffective one, the fake pill. And then the other 100 are going to have the actual pill with the medication in it. So, like I said, each person is going to get one of those, and then eventually, we don't even know, but there's going to be 100 individuals, and they will belong to the experimental group if they end up getting the container with the actual medication, and then we'll have another 100 random individuals who get the sugar pill, and they'll belong to the control group. So in this case, hopefully you see in this explanation, I'm giving you this example, that neither the patient nor the doctor knows who really has the drug. So the person sitting at the table does not know if he or she is giving the sugar pill or the medication to the person in line. The doctor just provided all those containers. He or she doesn't know who is getting which pill. And then lastly, the patient is just getting a container with pills. And remember, these pills are designed so that the sugar pill looks just like the actual pill. They look identical. So it's not like you can tell just by looking at the pills which is which. They both look identical. Nobody knows which patients actually have the drug and which patients don't. So even the control pill, like I've been saying, gets a pill. Even the control group, gets a pill. If you think about the last example I gave you in the last video about the orchard, the control group didn't get any plant fertilizer. So it was so obvious to us that this was the control group because they're not getting any fertilizer. In this case, with a double-blind experiment, we cannot do that, because if an individual just does not get a pill, then we obviously know that that individual belongs to the control group, and that defeats the purpose of the double-blind test. Therefore, everyone is going to get a pill, so that it looks like everyone is on equal playing ground. So, like I said, the control group is going to get the sugar pill. So it's a pill. It looks just like the one with the medication in it, like I said, but it just has sugar. It's made of sugar instead of the actual drug that's put in the medicine. And you might be wondering what this is called, and you might have even heard of it, because I remember I was introduced to this concept of giving the control sugar pills, and them not knowing that they're receiving a sugar pill in a double-blind test. This is called the placebo effect. In the simplest way I can put it, the placebo effect is when you give something to someone, like a pill, and they're convinced that if they take it, it'll cure their disease, but they don't actually know whether or not that's a sugar pill. So what happens is, if I end up giving this container of pills to a person, and I know that this container has sugar pills in it, but I tell that person this container definitely has the pills with medication, and I convince them, and they don't know, and they take those pills. They will actually convince themselves that they are taking the medication, and that they will actually, like, it's I know it's psychology, they'll actually try to see if they're showing results of getting better from their disease. So that's the placebo effect. Just keep that in mind. That's going to be an important term you're going to have to remember. If you see over here, I included two pictures. Here's a double blind. So if you see the patients, like these are two patients right here, blindfolded, so they don't know if they're getting the sugar pill or the actual pill with the medication. And the doctors, who's the experimenter, over here, he is also blindfolded because so think of it, he in both of his hands he's holding a sugar pill and then sugar pill and then the actual medicine. And then he closes his eyes, and the other two people are closing their eyes, and they're picking from his hands, and nobody knows which is which. For example, I think this here says the control, so this blue pill up here is the control pill, and it's going to this individual, but he doesn't know he's getting the control pill, and doctor also doesn't know that. Down here, the red one is the actual experimental pill. The doctor doesn't know this individual is getting it, and he also does not know he's receiving it. So I think this is a really good picture of the double-blind experiment. Down here is a picture from the study.com, and as you can see here, they're just showing the little container you usually get, like when you go to CVS or something, of pills, of your medication. And here we have the experimental group, and they're actually getting medication, and the control group here is not getting the medication. Instead, that's why they put an X over the actual medication. Instead, they'll get something that looks exactly alike, but it's just going to be a sugar pill with no medication in it. So let's continue the double-blind test. Sorry. Now you might be thinking, so since the control group is given a sugar pill and the experimental group is given the actual medication, how do we actually determine if the medicine was effective if we don't know who got what and no one has any clue? The doctor doesn't know who has which pill, the person who handed out the pills doesn't know who has which pill, and the patients themselves don't know who has which pill. So how do we figure that out? Well, data are coded so that treatments are unknown until the final analysis is done. I don't really have specifics on this, but there's always a way to determine who got which pill. Maybe by analyzing like I don't know, like their blood sugar content, or it honestly just depends on the situation. So in this way, data are coded. So at the end of the experiment, we're able to figure out who got which pill. So there is data telling us this container has either sugar or medication in it, and that all is coded, so it's not revealed until the very end of the trial. So let's say the trial lasts for a month. So after that month, then that data will be uncoded to see who has which container and who has which pill. And then the treatments are, like I said, so that the treatments are unknown until the final analysis is done. So no one knows who has which pill until we are ready to do a final analysis, until we're ready to collect our results and then actually look at them. And that is how we use this double-blind test. But before I end with the double-blind test, I do want to bring something up. The fact that the double-blind test does raise an ethical issue in the medical field. Like I said, the double-blind test is primarily used for clinical trials, and this raises an ethical issue, and you might be wondering why. So patients must be told that this is a trial and that they might or might not be receiving real treatment. A lot of the time in these tests, we have individuals with new diseases or rare diseases that still don't have cures. So the answer is really not simple as to just giving them a prescription, having them go pick it up from a pharmacy. So what happens sometimes is that doctors give their patients medication, but they don't tell the patient that he or she is part of a clinical trial, part of a double-blind test like this. So the patient is genuinely convinced the doctor believes in his or her individual welfare and that he or she is receiving a medication that will cure his or her disease. Therefore, it raises an ethical issue. So patients must be informed. This is a part of patient consent. And I know I'm kind of branching off into medicine, but I feel like a lot of you are here interested in biology because medicine is a path you're considering. So I do want to talk about that, like some ethics. So the patient should be told, patient consent, that this is a trial. So they should be told by the doctor that you're going to be part of if you consent, you will be part of a trial because we're still developing this drug to combat the disease you have. And then They have to also be told that this is a double-blind test. So they might be receiving the medicine or they might be receiving a sugar pill. If they receive the medicine, they could be receiving potential treatment to cure their disease. If they are receiving the sugar pill, it's not going to help cure their disease. So it's not going to make their condition any better. So they need to be told that. Additionally, scientists must also know what chemicals they are putting in the bodies of the experimental group. Therefore, scientists have to have the consent of the experimental group before they start administering these medicines. So they need to raise concerns like, these are the potential effects of taking this medicine because you are our first trial group, or this has happened in the past with people who were part of the experimental group. You need to be aware of the risks. So they must be aware of what chemicals they're putting in the bodies of their patients. And I wanted to include this picture down here because a lot of the time what happens is people who take the sugar pill, especially people suffering from things like diabetes, sugar pills can be detrimental to health because they can make your blood sugar levels fluctuate, and they a lot of the times people actually suffer from taking these sugar pills. So that is a drawback to the double-blind test. Additionally, if you see this man, let's just imagine that he was suffering from a chronic illness, one that needed to be treated immediately, and his doctors forced him to be part of a clinical trial. In that trial, maybe he was not part of the experimental group. Because think of this as a double-blind test. Maybe he ended up getting the sugar pill. And after getting the sugar pill, it really did nothing to help his condition, and his condition actually deteriorated because he wasn't getting a cure for his disease. And then by the end of the experiment, he was fatally ill because he did not get a true treatment. That's another drawback to the double-blind test. Okay, so other than actually, so I wanted to go over the double-blind test because that is a component of actually executing your experiment. So in the last video, we talked about coming up with a procedure. Now we just talked about actually executing that procedure. So going through that procedure. So after we do that, what do we do after we collect results? So we have to analyze them. And here's a really cool diagram that is part of the actual notes I got from school. I just clipped it and I included it in here so you all could see it. So imagine that. So I'm going to be shifting gears. So keep that. I really want you all to keep that last experiment I talked about in your mind, but think of this as a new experiment. This is called studies in genetically obese rats. So think of scientists as collecting a bunch of rats who are genetically obese, so very fat, and putting them in a laboratory and conducting studies on them. So I know these words might look a little daunting, so I'm going to break them down for you. So the scientists are administering two kinds of substances to these rats and trying to see what will help them the most. So first, I want you to take a look at glucose metabolism. So glucose is a type of macromolecule found in the body. Glucose is what we consider a carbohydrate, and carbohydrates are also sugars. Glucose specifically is a monosaccharide. It is a 6-carbon sugar, and it's usually found in ring structure. And if you don't know what I'm saying, that's totally fine. Think of glucose as a kind of sugar that helps with energy in the body. And metabolism obviously is the energy pathways in your body. Metabolism pretty much regulates the formation, the breakdown, the synthesis, the breakdown, the conversion of energy molecules like glucose. So this is pretty much talking about energy. So breakdown and conversion, synthesis pretty much means putting together, so building. Synthesis, breakdown, and conversion of glucose. So that's what this chart is talking about. So it's pretty much showing how effectively these rats are able to break down and convert glucose into usable ATP, which is the energy molecule we use to just drive our biological functions, like everything that goes on in our body. Here we have another graph to complement it. It's called HDL cholesterol levels. So HDL stands for high density lipoprotein. And lipids and proteins, so if you think of the word lipoprotein for that L, lipids and proteins, those are also macromolecules. Like I said, we're going to be learning that right after this video, we're going to go into macromolecules, I believe. But this is a type of cholesterol, and HDL cholesterol, this high density lipoprotein cholesterol, is good for you. It's the good cholesterol in your body, unlike LDLs, which are bad cholesterol. So this cholesterol, pretty much what it does is it absorbs the cholesterol in your body, it goes to your liver, and then what it does is your liver will flush all of that cholesterol out of your body, so there's no cholesterol buildup in your body. So HDL helps with that. So what that means is we want higher HDL levels in our body so that there's no buildup of cholesterol. And if you look down, so like I said, this graph talks about glucose metabolism. This one talks about HDL cholesterol. Down here you see biotin. So biotin is a type of vitamin B. It's a version of vitamin B, and it helps a lot with the growth of your hair, skin, nails. It also helps with your body convert nutrients into usable energy like ATP. Some of you might even take biotin vitamins like those gummies. So that's what biotin is. CRPIC is chlorine picta something. Chlorine picta something like that. I'm sorry, I can't remember off the top of my head. But it pretty much this has been proven to help blood sugar levels in diabetics and just things like that. So what these scientists have pretty much done is they conducted two separate experiments. This is one experiment here. This is the second experiment here. In this experiment A with the glucose metabolism, they split their mice into three groups. So let's say they had 60 mice. They split them into one group and they split them into three groups. The first group just got biotin, so just that vitamin B, and then the second group got CRPIC. And then the third group ended up getting a combination of both biotin and then CRPIC. They got a combination of it. And if you look at the results, they show that biotin was the least effective in they show you how much was like administered to each of these groups, and then they just show you the effectiveness of the different of biotin versus CRPIC by itself versus the combination. Same thing's going on here. So if you see, I think the best way to explain this is that the doctors are trying to combine biotin and CRPIC and trying to see if they can come up with a new compound that you can use as a medication that will help with glucose metabolism and HDL cholesterol levels. And here's a cute little rat I included off to the side. But it's okay if you didn't understand everything I said. What I wanted to show you is that when you analyze results, you're going to make graphs like this, just ways that you can digest all of that data you get. Because remember, you're going to be getting a large volume of data, so you need to give a visual depiction so it's easier for you to look at graphs like this and determine what actually is going on. So you can actually analyze your results. So you can look at so obviously this graph is not telling me, oh, biotin is more effective than CRPIC, or the combination is more effective than one or the other alone. I'm looking at the graph and I'm interpreting those things. So that's what analyzing results pretty much is. Okay, next I want to continue with the scientific method really quickly. So after you do your experiment and you collect your results, you need to analyze these results like we just did on the last slide, and then you want to write your conclusion. So your conclusion is pretty much your analysis is pretty much you interpreting what your data means. So and then your conclusion is pretty much you using that data to either say your hypothesis was correct or incorrect. So after analyzing your data, if your results end up supporting your hypothesis, meaning what you believed was going to happen at the end of the experiment, if your results validate that and support that, then what you want to do next is you don't want to just settle on that. You don't want to just say, I'm correct, my hypothesis is correct, this is period, this is done. That's not how science works, and that's just not the nature of the scientific method and experimentation. What you want to do is you want to repeat the experiment to validate your experiment. So you want to do as many trials as possible, because I'm going to talk about it down here with repeating trials. Actually, I'll talk about it right now. So you want to repeat your experiment. So you want to do as many trials as you can. So more trials results in a higher volume of data to support or refute a hypothesis. So the more trials you run, the more data you get. And in science, quantitative data, that is like gold. That is the currency. That is going to help you support whether your hypothesis saying it's correct, or refute somebody else's hypothesis and say, no, they're incorrect and I'm correct. So the more experiments you run, the more data you can collect, and the more evidence you have down here to back yourself up. So you can always just present these results and say, this is why my hypothesis should be accepted, or this is why your hypothesis should be refuted. Just something to keep in mind. And if for some reason your results do not support your hypothesis, do more research to form a new hypothesis. And I want you all to keep in mind, especially when you're in class, when your teacher is asking you to do an experiment, at the beginning of the experiment, he or she is asking you to write down your hypothesis based on some background information you know. It's okay if your hypothesis is not correct by the end of the experiment. That's totally fine. It is your educated guess. So we're already trusting as teachers are trusting that you've done background research on the topic you're experimenting on. And and that is reflected in your hypothesis. So if you give a very good, solid, educated hypothesis, then the teacher can tell that you did put thought into this. You did do background research on this. So what happens is if your results end up not matching your hypothesis, meaning they just don't support your hypothesis, they actually support whatever is opposite to your hypothesis, all you want to do is you just want to go back and repeat the process. You want to do more research and see possibly why your hypothesis was wrong. And then you might want to form a new hypothesis. Either you alter your current one or you just trash it and you form a new one because you see that the more research you've done, the more you believe in something else. And this is the last slide, but I just want to finish off the scientific method. So the scientific method, the very last step of it, a lot of the times I don't see teachers include this, is developing a theory. So usually scientists who have spent many years of their lives focusing on a single kind of experiment, like that clinical study with the medications, usually those are very, very large scale projects. So after doing something like that for so long, usually you want to develop a theory, a scientific theory. And a theory, in essence, is a collection of related hypotheses that have been tested many times, so they're broader in scope. So usually you'll have a topic, and then you'll have many scientists who have done experimentation on that topic because it's probably a significant topic, and then they've done many experiments of their own, but some way all of these hypotheses are related, and they all end up leading to one conclusion. So I'm trying to think of a good example. So let's just use that example I talked about in the last video with the apple trees in the orchard. Let's say like I said, I'm a farmer who took my own orchard and I did that experiment and I found out that I'm just making this up, but using no plant fertilizer ended up being the most effective way to grow plants and have plants yield the best fruit. Let's say this becomes a very popular experiment and many people across the world end up doing this experiment and they all end up getting similar or same results to me. So what happens is all of our hypotheses will be collected together and we've all tested these hypotheses many times in a broad scope. Maybe we use we use different kinds of plants and we do all these different things. But in essence, we're all collecting all our hypotheses and we're coming up with a theory that maybe plant fertilizer is not the best way to grow plants. So I'm just trying to give you an example. So again, a theory is a hypothesis that has been tested several times and results are reproducible by other scientists, meaning other scientists can also do the experiment that you did. It's not a super whack experiment. The procedure is clear and the results are reliable, meaning you get similar or the same results every time you do it, no matter who the experimenter is. And lastly, after a theory is developed, the theory can be disproved, meaning someone can end up doing the experiment and get results that actually refute it, so results that prove the opposite of what the theory is actually proposing. It can be changed, meaning maybe there are components of it that need to be tweaked a little bit, or it can be entirely replaced. So let's say or falsified, so proven false, so proven untrue in all scenarios. So in that case, a scientist who has disproved your theory would end up coming up with an alternative theory that ends up replacing the original theory because the alternative theory is actually true and the original theory was falsified. Lastly, I want to go over what a scientific law is. So obviously, oftentimes you see theory versus law. Theory is uncertain, law is certain. A scientific law cannot be disproved. It has no counterexample. It is always true. And I think the best way to explain this are through the two pictures I have here. On the left is a picture of our solar system. You see our planets and the sun. And what keeps the planets attracted and in orbit is gravitation. So gravitation was a concept developed by Newton. It's when two bodies are attracted to each other, and that attraction, I think, is dependent on the mass of those objects. So what happens, the thing is, that is a proven law. Like Newton has proved that. And that's a prime example of that is our solar system. over here you see something exploding in space, and I tried to find a picture of the Big Bang Theory. So the Big Bang Theory is a theory of creation of our universe. Scientists Some scientists believe that the universe was created with a big bang, so everything just exploded and just formed. The reason this is considered a theory is because we can't prove it yet. Yes, I've done research, and there are actually two scientists called last name Wilson and Penzias, I think that's how you pronounce it. They have found radioactive material in the solar system by using radio telescopes, I believe. And they've found radioactive material that maybe supports this Big Bang Theory, but there's nothing legitimate proving it. If that makes sense. So that's all I have for you today. I hope you enjoyed the video, and I hope it was super informative. We are done with the scientific method, and we will be getting into macromolecules next, which is a super complicated but extremely enjoyable topic for me. So I look forward to teaching that to all of you. If you enjoyed this video, please like and subscribe and hit the post notification bell. Drop a comment down below and share using our socials, which are Facebook, Twitter, and Instagram. If you have anything personal or business related that you'd like to discuss with us, please email us at eCoreAcademy@gmail.com. And lastly, our website has gone up. Please check it out. It has a bunch of good, sweet functionalities that are available there, but not on the YouTube channel, such as notes for you to follow along with these videos with and fill in. Answers to those notes, quizzes, all of these videos organized into courses for you to follow, and so much more. So I highly recommend you make use of that free platform. So that's all I have for you today. I hope you enjoyed my video, and please look out for the next biology related video I put out. Bye. Have a great day.